According to my clock, it's 9 o'clock. Good morning. My name is Mike D. Lecluse. I'm president of Lesman Instrument Company. I'd like to thank all of you for taking the time out of your busy schedule to join us for today's webinar, which is Tank Blanketing 101. Today's presenter is Harry Woebkenberg. Harry is a product manager for Richards Industries, which owns Jordan valves as well as low-flow control valves, Marwin valves, hex valves, Steraflow, and Vestabel steam traps. Harry joined Richards in 2008 and has been in the valve industry since 2002. He also has Lyle Hamilton with him. Lyle is the senior engineer for Jordan. Today, Harry's going to cover what tank blanketing is, why it's important, the applications, products used, some do's and don'ts, and some sizing and selection. Because of the large number of attendees, we have the phone lines muted. If you have a question, there is a chat tool in the GoToWebinar control screen that allows you to type in questions. So please, if you have a question, go ahead and type it in, and I'll get Harry to answer it for you. With that, I'm going to turn it over to Harry.
Well, thank you, Mike. Good morning, everybody, and welcome to Tank Blanketing 101. This is presented by Lesman Instrument Company and Jordan Valve. My name is Harry Woebkenberg. I'm the Jordan Valve product manager, speaking to you this morning from Cincinnati, Ohio. Joining me is Lyle Hamilton. As Mike said, Lyle is our senior Jordan Valve and low-flow valve engineer. We will present for approximately 25 to 30 minutes and then answer any questions that you may have. A complete blanketing and safety valve system would require a variety of products, including padding and depadding valves. Normally those are regulators. Pressure and or vacuum vents, emergency vents and valves, and flame and detonation arresters. It would require several sessions to cover all the individual components and their function. So today our discussion will focus on padding and depadding, the primary components in a double-sided system. By definition, tank blanketing, sometimes referred to as padding, is the process of filling the empty space of a liquid storage tank with an inert gas, most likely nitrogen. Nitrogen is normally used in blanketing applications because it is readily available, relatively inexpensive, and inert. Why is tank blanketing important? Blanketing protects people, the environment, product, and equipment. If the media is combustible, blanketing removes the oxygen required for combustion. As you all probably know, combustion requires oxygen, heat, and fuel. The fuel cannot be eliminated if it is in fact the liquid that's inside the tank. A static charge or lightning might be able to provide the heat source, but by isolating the oxygen in a blanketing application, we can reduce the risk of fire. Blanketing also protects food and other substances from oxidation, contamination, or evaporation. Vapor recovery in some systems will prevent harmful vapors from escaping into the atmosphere, and reducing corrosion through oxidation helps maintain the integrity of the tank. Who uses tank blanketing? Tank blanketing is a quick, fast-growing market. The bulk of tank blanketing applications are in the chemical, petrochemical, and oil and gas industries. Probably 80 to 85% of all the tank blanketing applications are in chem, petrochem, or oil and gas. Industries with a smaller percentage but using tank blanketing nonetheless are food and beverage, pharmaceutical, biopharmaceutical, and the semiconductor industries, and a variety of products are protected in the market segments listed above. You have everything from adhesives, catalysts, various chemicals, deionized water, water for injection, volatile combustibles, solvents, soaps, sealants, fats and oils, flavorings, foods, fragrances and health and beauty, juices, and the list goes on and on. So again, a number of products are affected through tank blanketing in a variety of industries. One of the keys is when we're blanketing a valve, and we'll talk a little bit about the operation, but the nitrogen blanket that's put on top of the media in the tank will vary. The volume of media in the tank will vary due to a variety of factors. Things that pumping media in or pumping media out, temperature increases or temperature decreases, air or moisture entering the tank, or in some cases vapors escaping the tank. As the volume changes, the vapor space in the tank will change as well. When we're looking at tank padding and de-padding in a two-sided system, tank blanketing, or the padding side, when the vapor pressure in the tank drops below the preset limits or below the set point, the regulator's diaphragm moves the plug away from the seat, allowing the blanketing medium to flow in. The vapor recovery, or the de-padding side, this is going to be at a set point slightly higher than the tank blanketing valve. When the regulator moves the plug away from the seat in response to higher pressure vapors, and this allows excess vapors to flow out of the tank. Once the blanket is established, additional gas must be added to compensate for the cooling, pumping product out of the tank, and to compensate for any leaks. And if more liquid is added to the tank, the rising level will force the blanketing gas out of the vent valve if it is in a single-sided system, or it will be moved by the de-padding valve if it's a double-sided system. As you can see here, these are different ways that the pressure is going to decrease in the vapor space. When the vapor, or when the pressure decreases in the vapor space, your padding valve, or the pressure reducing valve, the regulator that's going to feed gas into the tank, will open and supply more gas into the tank. So ways that happens: if we pump product out of the tank, if the temperature drops, or if emissions escape the atmosphere. Those are all ways that the vapor space is going to be increased and the vapor pressure, the blanket pressure, decreased. How do blanketing valves work? Blanketing valves are pressure regulating valves, PRVs, and they're also commonly referred to as padding valves or makeup regulators. The regulator is controlling the pressure inside the tank. The regulator will sense a decrease in the pressure and will open to introduce more gas and moves to the closed position when the pressure returns to the set point. The blanketing gas supply line is connected to the tank via an inlet pipe. What valve should you use? There are several choices available in the marketplace. There are self-operated or direct operated valves. These offer fast response, the lowest cost of any of the available choices, and generally speaking, they're fairly simple in design. Pilot operated, high flows, extremely accurate, and very fast lockup. So normally, pilot-operated valves always should be used in a one-sided system, and can be used in a double-sided system as well. But this can all get a little bit confusing, but when you understand the capabilities of the various valves, it will make selection a lot simpler for you. And a little bit later, when Lyle gets into the sizing and actual selection, this should all make a little more sense. Self-operated valves are very sensitive due to the large diaphragms, very light springs, set points as low as 1 inch of water column, and they can either have an internal or an external pressure register. This is an example. This is a cutaway of a self-operated valve with an internal pressure register.
And I might add that if you look there, you'll see a little tube. The flow in this valve, as shown in the picture, is from bottom to top, and you'll see a little tube that looks downstream of the pipe. That actually aids in performance to help get the valve open when the pump starts. As the gas flow starts to speed up, what it will do is it will communicate that pressure very quickly up into the sensing chamber so that the valve can get itself open. And the last thing you want to do is pull a vacuum on the tank when the pump starts up, and that's one of the features that we have here in our Mark 608 IS, which stands for internal sensing, or improved sensing, to keep that from happening.
Okay, also available in self-operated versions are higher flow versions, balanced plug, which will allow you to handle higher inlet pressures while still regulating down to inches of water column. Double-seated versions, again for higher pressures and higher flows. And for very low set points, 8 inches of water column or lower, it's often recommended to install the valve in the inverted position.
Yeah, that means your closure cap and your adjusting screw are on the bottom of the valve instead of the top, and the reason for that is that we are using the force of gravity, which has proven free and reliable over many years to help us operate the valve and to get the valve shut off quicker when the tank approaches the set pressure.
Yeah, we're going to talk a little bit here in a minute or two about the sensing line, which the installation and positioning of that is very important, and there are several guidelines that are worthy of serious consideration when you install these valves. But you can see here that the first valve that we looked at, and we're going to spend a little more time on the internally sensed valve. This actually has an external register, and you can see here, if you can follow the arrow, I'm circling where the actual sensing line would be attached. That's a 3/4 inch FNPT connection that's right there on the valve. Internally sensed, and again, the reason that these valves are so sensitive is due to a large elastomer diaphragm, 6 spring ranges, and the springs in these valves are extremely light. And again, in most versions, most manufacturers offer from 1 inch or 2 of water column up to maybe 1 or 2 psi. Generally, are the spring ranges, but within that small range, again, most manufacturers will have anywhere from 3 to 6 different ranges over that very small range. There's a lever arm in here that's going to amplify the diaphragm forces for tighter shutoff. These valves can be oriented. 360 degrees. It can be installed in any position and easily repositioned while in line. Lyle touched on this aspirator, this pitot tube, okay, and it's designed and situated to optimize the boost effect and improve performance. In this particular valve design, no sensing line is required. So this is probably the simplest type of blanketing valve that's available in the marketplace. Flow will come here, and what we're doing is we're sensing the downstream pressure, and again, that's sensed up through this stainless steel pitot tube, and when the pressure underneath the diaphragm overcomes the spring, then the valve will move to the closed position. A soft elastomer plug provides tight shutoff. Here's a balanced plug version, and the difference here, it's very similar to the internally sensed. There are two significant differences. One, this is externally sensed, and this is an MPT sensing port where your sensing line would be connected. And the other is that you actually have a balanced plug. And because of the balanced plug, you can handle higher inlet pressures and still control down to set points that are in the inches of water column.
You'll notice when we start looking at our sizing charts, you'll notice for instance, with the 608IS product, as the set points get lower, you'll see some of the chart is grayed out as you go out toward the right-hand side where you're having higher inlet pressures. This valve will have much more flow capability out there, or the ability to at least operate in those ranges, maybe not flow more, but it will get you into those ranges where you're using set points up to over 100 psi and down to only 2 inches of water. That gets a little difficult, so that's why on this one the plug is balanced, but in order to do the balancing design, we had to take away the internal registration and switch to external. So that's what the 608 BP is for. That stands for balanced plug. That allows you to get those 2-inch water column set points with higher inlet pressures than you'd normally get with the 608IS.
Okay, double-seated versions are also available in the marketplace. Again, the double-seated design allows the valve to handle increased flow and higher pressure drops than similarly sized single-seat designs while maintaining that tight shutoff. So again, large diaphragms, several spring ranges, very high flow capabilities. In this valve, this type of valve, you can get up to almost a,
I believe we have 19 CV on our tube.
Yeah,
17 or 19.
17 or 19 CV, so fairly high flows in this particular version. Pilot-operated valves. Pilot-operated valves have extremely high flows, very fast lockup, and are extremely accurate. The reason that we talk about, first when we talk about the self-operated valves in a double-sided system, when those valves go to the closed position, they don't fully lock up until anywhere from 4 to as many as 10 inches of water column over the set point. So always coming through there's what is called a freshening flow until they physically lock up. But in a double-sided system, you have a back pressure regulating valve or a D-padding valve. And the D-padding valve set point will be a few inches of water column higher than the padding valve. So what you don't want to do in that is put a valve that has a fairly long lockup into a single-sided system, because you'll be kicking off emergency vents, and people, obviously operators don't like that. So that's a consideration and very, very important point. Pilot operated valves lock up very quickly, and so they're more suited to single-sided systems.
Yeah, the difference is that you'll see a pilot operated valve go full bubble tight shutoff once the pressure gets to 2/10, that's 0.2 tenths of an inch of water above the set pressure, whereas you need a lot more than that to lock up a simple direct operated regulator. So if your customer does not have a D-padding system and doesn't need that freshening flow through the tank or a constant throughput to carry away corrosive vapors and so on and so forth, if you're just putting a pad on the tank, this is the valve you need to use.
Okay, this is just a cutaway version of the valve that was pictured in the last photo, but you can see this is an internally piloted valve. Okay, you have an internal pilot. The plug is normally closed when the tank blanket pressure is at the set point. It's held down against the inlet pressure by the return spring.
And by inlet pressure.
And the loading of inlet pressure through a restriction into the chamber above port A. So this is just a cutaway, slightly different look, actually significantly different look than the self-operated versions. A little more complicated, a little more cost involved in this, but again, very high flows, very, very fast lockup, and extremely accurate. This is a picture of another pilot-operated version where you have here the main valve body and actuator are designed to handle high inlet pressures and high flows. So on a 2-inch version of a valve like this, you can flow about 250,000 SCFH. On this particular valve, 45 CV in a 2-inch version. Some versions that are available in the marketplace in larger diameters can flow more than 2 million SCFH. Massive flows, obviously large valves, but those products are available in the marketplace. When the flow comes in, again as high as 200 psi, there is a conditioning regulator, and normally it's a globe-style regulator, and it will drop the inlet pressure to between 15 and 25 psi, and that feeds the pilot regulator. In this configuration, the pilot regulator is actually a tank blanketing valve. So only a few manufacturers make this, but this is a valve too that is well suited for single-sided applications. I briefly stated that we wanted to cover some important considerations when you install this type of product. The control line should slope downward toward the tank and to prevent condensation buildup. The control line should be as short and straight as possible. The control line needs to be connected to the point where the pressure is to be controlled, and the pipe size should be increased 1 pipe diameter for every 10 feet of control line when you have set points less than 5 inches of water column. In addition to those considerations, the regulator should be kept as close to the tank as possible and as high as possible. Minimize the length of the downstream pipe coming from the valve. Never reduce the pipe size on the valve outlet to the tank. In any downstream isolation valve after the regulator must be a full port type. Sensing line should be a minimum of 3/4 inch in diameter. A full port sensing, that shouldn't say ling, that should say line. Isolation valve is recommended, and again make the sensing line as short and straight as possible. One of the first service calls I ever went on as it relates to padding or depadding valve was at a nuclear power plant in China, and they said the valve wasn't working correctly, and I got up on top of a 20-meter tank along with a couple of their technical people, and there were no fewer than 6 elbows in the sensing line. And so as you can imagine, the valve wasn't really sensing the pressure as it should, and therefore it was not functioning correctly. So again, short and straight as possible, no restrictions. Always good rules to live by, and you'll find that the performance in your valve will be much better, or you'll actually optimize the performance of your valve in that case. So we looked at adding to your nitrogen blanket. How about depadding or taking some of the blanket away.
Hey, Harry?
Yes.
Before you jump into that, we do have a question.
Okay.
And the question is, what do you mean by the lockup on the pilot actuated valves?
Lockup, when any regulator, downstream regulator, and a tank blanketing valve regulates downstream pressure. When you're flowing, when the flow starts to stop, the only way to make the flow stop is the pressure starts to rise. There is a point where the plug just hits the seat and the flow essentially stops, but there's maybe 1 or 2 SCFH or maybe as much as 3 or 4 still going through there. And in order to make it fully shut off, you have to pull the, lack of a better word, pull the seat up a little harder onto the plug to fully shut the seat off. And that means the pressure has to rise a little bit over the set point for that to happen. On a simple regulator, the only force you have available to you is the tank pressure itself to shut it off. Whereas on a piloted regulator, the pilot can use the energy of the upstream pressure to actually shut the valve off hard. So it shuts off much quicker and it shuts off much tighter. In other words, with respect to climb above the set point. What you'll see is probably a 10x advantage with a piloted valve over a self-operated valve. In other words, you might have to go 2 inches of water above the set point to lock up on a conventional self-operated unit like a 608 IS, whereas on the 688 or the Cumming 695, you're talking about 0.2 inches of water in order to produce a bubble-tight shutoff.
Mike, does that answer the question? Is that?
I believe it does. Thank you.
Okay, great.
If it doesn't, Doug, who asked the question, feel free to expand on your question and send it to me.
Okay, perfect. So now we're going to look at the D-pad side. So what happens when more product comes into the tank, the temperature rises and the media expands, or air and or moisture get into the tank as a result of the tank not being totally tight. What happens is the vapor space then will decrease and the pressure will increase. So at this point, we're going to have to get rid of some of the pressure that's in the tank. So how does the depadding valve work? This is a back pressure regulating valve, a BPRV. The valve also, like the PRV, is regulating the pressure in the tank. As I stated earlier, you'll have the inlet valve or the padding valve will have a set point, for instance, of 2 inches of water column. Generally, the depadding valve will have a set point that's anywhere from 4 to 6 inches of water column. It's set slightly above the other, so as the pressure rises, then this valve will open and relieve the pressure to the tank, either to atmosphere or for reclamation in some form or fashion. And an outlet pipe is connected to the valve and to the tank. What valve should I use? On depadding valves, generally speaking, there are fewer choices available in the marketplace. In most cases, with most manufacturers, I can speak from our experience here, the ratio of padding valves to depadding valves generally on an annual basis will run 5 or 6 to 1. So, and again, that will depend on whether or not you have a one-sided system or a two-sided system. If you're using self-operated valves, in general, you want to make sure that you have a padding valve as well as a depadding valve. But there are self-operated versions and pilot-operated versions out there together. And again, as depadding and padding work together, the padding valve or the pressure-reducing valve is controlling the pressure in the tank, as is the depadding valve or the back pressure regulating valve. The padding valve ensures there is sufficient pressure in the tank And the depadding valve ensures that there's not too much pressure in the tank. And again, the set point of the depadding valve is slightly higher than that of the padding valve. Now I'm going to let Lyle hop in here. We're going to talk about sizing these valves, the significance of API 2000, and so I'll let Lyle take it from here.
Okay, good morning, everybody. API 2000 is a standard that gives a quick, uniform, convenient way to handle sizing. And the tank blackening valve set point, the set point is determined by the manufacturers of the tank, and the capacity requirement of the blanketing valve will be composed of two components. One of them is in-breathing due to product movement out of the tank, and that's pump out, or you actually have in-breathing due to vapors and product in the tank contracting due to cooling, such as the sun goes down, weather changes, etc. So those are the two things we need to allow for, and API 2000 just gives you a quick walk through there. Step one, we're going to determine what we're going to call Q displacement, and what that and your customer will need to tell you how much or how fast he can pump liquid out of the tank. And let's say he comes back with an answer of 15 GPM. To calculate Q displacement and SCFH, you just multiply the maximum pump out rate in gallons per minute times 8, and then that will give you Q displacement in standard cubic feet per hour. So in this example, we're looking at 120 SCFH, and that's part one of our answer. So we'll calculate that and write it down. Then we move on to step 2, which is going to be what we're going to call Q thermal. That is the in-breathing capacity due to the tank's temperature, both the media inside the tank cooling down, the nitrogen blanket itself cooling down, and the outside of the tank cooling down. And customers say, well, tank is insulated. Well, so is my house, and so is your house, but when the furnace goes out, it's going to get cold. And we need to account for that. So the first thing we'll need to do is how much can the tank hold when it's full? And let's say in this example, your customer comes back with 84,000 gallons. Barrels is another common way of measuring tank capacity, and the standard gives you the numbers in both barrels and gallons that you need to use for your in-breathing allowance. So for English units out there, for going in gallons or traditional barrels, it will tell you that an 84,000 gallon tank is going to require 2,000 SCFH for in-breathing. Step 3, you simply add Q displacement and Q thermal together for a Q total requirement of 2,120 SCFH. So now we've determined what the capacity of the valve has to be. So we're done there. Now we move on to step 4, and we'll need to select a suitable valve. We'll need to know what the gas supply pressure is and the desired set point in the tank is. And the gas supply pressure usually for these is going to be coming off of a liquid nitrogen storage facility, running through a vaporizer and a heat exchanger to warm it up a little bit. So let's just say your customer's coming in with a 60 PSI nitrogen supply, and he wants a 2-inch water column set. That's not uncommon, and your Q total that we calculated is 2,120 SCFH. As you go through our products listed under tank blanketing, you'll notice that one of the selections available in addition to the cut sheet and the dimensionals is the API 2000 sizing guide. And it goes through all those charts and tables that I mentioned that you used in steps 1 through 3, but it also has flow charts listed for all the products we offer for tank padding. And so we now know that we've got a 60 PSI nitrogen supply, we've got a 2-inch water column set, and we need to flow 2,120 SCFH of nitrogen. Well, as we start going down through our products, we find on page 5 that our 1.25" marked 608 IS can flow 2,800 SCFH with a 1/4 orifice at those conditions. So that's a good match. It's over The valve capacity is over Q total, but not by a huge amount. So that's a good pick for us. So we would go ahead and spec out an 1¼ 608 IS, order it with a 1/4 inch orifice, and then of course you would select the diaphragm and seat material based on what the material compatibility is with the liquid in the tank. And the reason for that is there's still some fumes and vapors that can get up into the sensing line and into the valve itself. So the elastomer seating and the elastomer diaphragm need to be compatible with what's in the tank. Some of the charts are normalized for air. Some of them are normalized for nitrogen. If you find one that shows air, simply multiply that number by 1.018, and that will give you the flow in nitrogen. There's not a whole lot of difference in between the flow, but you know, when you're talking about bigger flows, like when you get into bigger tanks requiring 15,000 to 20,000 SCFH, that small difference can start to become large enough to where you need to pay attention to it. So just remember that factor.
Okay, so that concludes the presentation portion. Now we can look and see if anybody has any questions.
We have questions.
Okay.
We do have questions.
Okay.
Let's run through the first one. Is a special tank venting required for nitrogen blanketing? And the question is continued by, is an unregulated gooseneck venting adequate?
There's a lot of accessories that you need when you're going to do this. One of them is going to be, you'll need a valve that can, if there is an emergency, for instance, like a failure of the padding regulator itself, you'll need an emergency vent to relieve that pressure if the valve fails to shut off or gets damaged. Also, if it were for some reason gets stuck and fail to open, you need a vacuum braking type of vent in there to keep from pulling the tank inward on itself as you pull the contents out. So the answer to your question is it really kind of depends on whether or not you're going, what your customer has. You need to have, at best, you have to have emergency venting to take care of the fact that the padding regulator could fail or the nitrogen supply could fail, or that there could be damage to one of those two systems. So your emergency vent would keep the tank from overpressurizing during a filling operation, or it would keep it from becoming a vacuum situation, which can be just as detrimental to a tank because of a draining operation when the nitrogen supply failed or the padding regulator failed. There are valves that they have combination valves. They call them. They have what they call conservation valves, and they're a complete system of accessories out there separate to the padding and depadding itself that have to be on the tank. Detonation and flame arresters are another one if the tank's contents are flammable, like for instance gasoline would be a great example. So there's all kinds of accessories other than a padding regulator and a depadding regulator that are going to have to be present on the tank as part of the total system.
All right. In general, how often do blanketing valves have to be calibrated or serviced?
Well, that would depend on how, obviously that depends on, like with any valve, how often it gets actuated and to what extent. If the tank is constantly being filled and drained, and you're constantly locking up, opening up, and locking up, obviously that's going to take take a little bit of the life out of the valve. Whereas if it's only filled once a day and drained over long periods of time, that's another thing. It's totally dictated by the environment and the application to which the tank is serving that's going to set that up. I would say, generally speaking, probably a lot less than you'd have to service a standard regulator, like for instance a steam service, for example.
Is that something that can be handled on site, or do they have to ship them in to be calibrated?
Once again, it depends on your customer's level of sophistication. Simple regulators can probably be handled in the field, and we can ship components to you. Some of the piloted regulators might be a little bit more difficult, and depends on if your customer is sophisticated, he may be able to apply a repair kit. If they're not terribly sophisticated or they don't have an in-house valve repair shop, you might want to send the piloted version back to us.
Okay. What is the benefit of depadding valve versus other methods of regulating back pressure, such as a conservation vent?
On a depadding valve system, what you can do is have a constant freshening flow. For instance, where you, like, let's say if you have a highly corrosive liquid in the tank and its vapors are corrosive, by having a slight constant flow through the tank, you can carry those vapors away via the depad system, and then clean that. You can separate them out of the nitrogen and then recycle your nitrogen. And also, it's environmental protection. You're not dumping any hazardous fumes out into the environment by simply allowing the blanket gas to escape during the filling process, or when you have the inverse of thermal cooling, when it starts to heat up and the tank needs to breathe out because the contents are getting hotter and the nitrogen is expanding. That nitrogen may be carrying some harmful vapors that has picked up from the contents of the tank out into the atmosphere. So that would be the reasons why you go with a depad system. Number one, reclamation of your nitrogen. Number two, environmental concerns.
All right. Can you comment on achieving microbiological control via nitrogen blanketing?
No.
No.
Nitrogen blanketing will, by taking away oxygen, kill most bugs, I would say. There are certain bugs that can, what they call anaerobically respirate. In other words, they don't need oxygen to survive, either for short periods of time or for longer periods of time. So for the most part, yes, nitrogen blanketing will stop or suppress biological activity in the contents being stored. It will not completely eliminate it.
Okay. Do you know if there's any literature that talks about, you know, how the nitrogen blanking affects microbiological growth?
I would suggest probably some of the food and beverage organizations, such as the National Sanitary people in the NSF group, and perhaps the ASME's bioprocessing group might have some literature available to you on that.
Okay. Would any of these valves work properly if installed upside down?
Now, in some cases, we do want you to install them upside down, and that's generally on the simple regulators where the set point is either under 8 inches or 4 inches, depending on what the inlet pressure is. As I said, you know, gravity, you can say two things about gravity. Number one, it's reliable, and number two, it's free. It will help the self-operated regulator lock up quicker, get that plug on the seat, and get the flow cut off much earlier than it would if the valve was mounted right side up. So we take advantage of that in our self-operated regulators. On other units, like some of the piloted regulators, we want you to install them as shown.
Okay. Where does nitrogen go when depadding with double systems?
Usually it goes into a reclamation system, and there'll be a slight vacuum downstream of the pad regulator. That's on its output side, the side it is not sensing. And what that nitrogen will go through some sort of a scrubber system to collect and remove any contaminants that the nitrogen picked up from the contents of the tank, and then it can go back into a system and be recompressed, reliquefied, and reused again.
Okay. Is there a protocol or procedure for testing the efficiency of the operating padding system?
Not that I'm aware of. I would suggest those might be more along the line into what you see in company codes. You know, depending on who the operator is, whether it's a chemical company, you know, a refinery, a food and beverage company, they probably all have their own separate company specified codes, or whoever their government regulator might be.
Okay. Here's the same question, just a slightly different twist on the reclaiming of nitrogen. Do we recycle into the supply nitrogen, or do we gather and dispose of it? I think you said there are systems.
I would imagine probably both. They can be recycled and then resupplied. The systems that do that, would have to be capable of detecting and removing whatever contaminants are in the nitrogen and the vapors that it has picked up as it went through the tank, or you may store it and hold it for later removal by some service. It would depend on, again, I would say what is in the tank and what level of sophistication the company needs, and the expense of recycling the nitrogen as to whether or not the individual tank owner-operator is going to use that or not.
Okay. If the gas blanketing valve is used on a silo with powders, do you need to have a slight flow of nitrogen gas in the sampling line to avoid anything getting plugged?
Yes, and we have what we're introducing with our 695 is what's called a purge option feature. What that consists of is, in addition to the hardware on the valve, what we'll do is we'll have a takeoff from the supply side of the valve going through a needle type rotometer that will meter off flow in very small amounts, like 0.01 to 0.005 SCFH, and then that output from that meter from the needle valve and the rotometer will then be keyed into the actuator's sensing line to keep a small amount of flow through there to stop corrosive fumes from coming back up into the actuator, or to keep powders from coming up into the actuator and then lodging themselves in there. So that'll be a cost added option, definitely available. The way you recognize valves like that is you see something that looks like a rotometer mounted on the valve. That's exactly what it is, and what it allows you to do is to set a small purging flow to keep that things like what you just described from happening.
Okay. One of the other questions was, can we get a copy of the presentation? This presentation has been recorded, and it will be reposted out to the internet, so you will have the availability to go and review it and look at it again. So that email will come out in the next day or two once it's posted. I think that's all the questions I've got. At least that's what it appears to be. So Harry and Lyle, thank you very much for your presentation. If there are any further specific application questions, feel free to give us a call at 800-9-LESMAN. If you do not know your account manager, feel free to ask for me, Mike DeLaCluse, and I'll make sure that you get taken care of. The next webinar will be held in late February. We'll send out an email shortly announcing what the subject is going to be. At this point, I think one more question has come in. So let me shoot out the one last question. How does back pressure affect the D-pad valve capacity?
Back pressure on the D-pad valve, i.e. downstream pressure from the D-pad valve, would tend to reduce its flow capability. And in our 508 products, you'll notice that normally there's a slight vacuum applied to the D-pad regulator, and we give you 3 instances. I believe it's no pressure, minus 2 inches of water, and minus 4 inches of water in there, and it shows you how that affects the flow. So if you have back pressure present, the answer is the flow goes down, and yes, it has to be accounted for. And that would be in the sizing charts that would accompany whatever valve you are planning to use.
Very good. At this point, there are no further questions. So Harry and Lyle, thank you very much for your presentation. Again, if any of our customers do have further questions, feel free to contact me. I believe you also get emails from me, so my email address is there. If you don't have it handy, it's miked@lesman.com. So at this point, since there are no further questions, we'll go ahead and conclude the webinar. Thank you again for taking time out of your busy schedule, and look for this to be posted if you would like to watch it again.
Yep. Thanks, everybody. Thanks, Mike.
Thank you.
Okay.
All right. Thank you, guys.
All right.
All right.